Okay, welcome everybody to the CUNY Representation Theory Seminar. So for our first meeting, we're happy to have Jacopo Gandini. We'll talk about on the multiplication of functions of reductive spherical pairs of type A.
Okay, so thank you very much to Josh and Bart for the invitation. So let me just plug the computer before it's late. So okay. So do you read? So there is, okay. Okay. Do you read? Do you see everything? Okay. So the title is there. So first, let me explain a bit the problem, and then we will see some cases and some conjectures and some theorems possibly. So we start with the G, which is a connected semi-simple semi-simple algebraic group over C. So for example, but I mean, this is a representation theory seminar, so this should be fine. We can take, of course, SLN C. Okay, this will be our, also in the example, I will stick to SLN and some of its subgroups. So what are we interested in? So first of all, to the reductive subgroups of G. So let's take K, a reductive subgroup of G. And what does it mean that GK is a spherical pair or that K is a spherical subgroup? So let's give this definition. So GK is a reductive, but I mean by assumption K is reductive, a spherical pair. If so, we have an homogeneous space associated to this pair, which is G mod K. And this is actually an affine homogeneous space, and this is equivalent to the fact that K is reductive. And we can look at this, this is a representation, these are a function over G mod K, and we have a natural action by right multiplication of G. So we can decompose it as a, we can look at it as a G module, and the point is that this is a multiplicity-free G module. If so, this collier ring is multiplicity-free. Now I will explain what does it mean as a G module. So what does it mean? Well, this just means that so we can decompose it into isotypical component, and this means that every isotypical component is irreducible. Okay, let's have a closer look to this definition because it makes things probably more clear. So let's look at there is a quite classic theorem. I mean, typically it's called the Peterweil theorem or some version of the Peterweil theorem. Namely, we can look at the functions of a G and we can decompose it under the action of G times G, acting both on the left and on the right. And this is the direct sum, let's say it's isomorphic, to the direct sum of V lambda, well, let's not use any notation I did not introduce yet. So this is just the direct sum of V dual tensor V, or if you want, of the endomorphism of V, where V is any irreducible representation of G, I mean finite dimensional and rational representation. Okay, but then if we look at the function over G mod K, these are just the K invariant function on G, K acting on the right. Namely, we are taking K acts on the V on the right, namely, these are V dual times the K invariants in V, where V. So in some sense, these VK, these invariant spaces are multiplicity spaces. So being multiplicity free just means that these VK have dimension either 1 or 0. Namely, GK is a spherical pair or the coordinate ring is multiplicity free if and only if the dimension of Vk is at most 1 for all irreducible representation V. Okay, and this is also quite a typical definition of these multiplicity-free subgroups. Okay, so let's have some examples. Well, the main example, I mean, well, not the main, but I mean, a fundamental example, a fundamental class of example is the class of symmetric spaces or symmetric subgroups. So what does it mean? That so we start with theta, an involution of G, an algebraic involution of G. So theta squared is equal to 1, and K is the set of fixed points, or rather the identity component of the fixed point of G theta. Then this is what is a classic theorem. The GK is a multiplicity free, is a spherical pair. Well, or rather a symmetric pair, but I mean, they enjoy this multiplicity freeness property. Okay, so more explicit example, and we will come back to some of these later. So we have, for instance, SLN over SON, or SL2N with SP2N, the symplectic group. Or also, well, some more sophisticated example is 6 over F4. Well, there are several, and so on. And well, not every spherical pair is symmetric. So let me give a few non-symmetric examples. So let me give 3 of them. So for instance, we have SL2n plus 1 over SP2n. Well, so SP2n sits inside the SL2n, which sits inside the SL2n plus 1. Or also we have SO2n plus 1 over GLN, or also SO8 over G2. This last one is famous because it's the triality. So it's kind of a generalization of the symmetric subgroups. This is the fixed point of an automorphism of order 3. If we look at the triality over D4, this is G2, a set of fixed points. Okay, and so on. I mean, there are plenty. Okay, so what is the problem? So we will concern with G, will be a simple group for us. I mean, simple as an algebraic group. So for instance, SLN is fine. I mean, almost simple sometimes it's called. Namely, the root system is irreducible. I mean, might have a finite center. So we can take the simply connected form or what we want. Okay, and we will consider spherical pairs for G. So K is a reductive subgroup of G with this property that this coordinate ring is multiplicity free. So we have a classification of this pair. So well, this is quite old. So we have a classification of Kramer in 1979 over the complex number. I mean, rather in terms of Lie groups, and also more recently there was a classification of Knopp and Rödle in 2015. So this is over C, and C is arbitrary. I mean, wait, sorry. Yeah, okay. So this is arbitrary characteristic. Okay, so actually, I should mention that there is a notion of spherical pair, which is way more general than what I said. And there is a classification of spherical subgroups in much bigger generality, but we're interested in this case. So I will stick to this. Okay, so what is the problem? I mean, all this classification in this case, but also in greater generality, they involved, I mean, in the last, well, almost 40 years now, there have been a lot of, I mean, a lot of geometric and combinatorial and algebraic structure which came out, and I mean, around this kind of subgroup. So, and I mean, all of this being part of this classification. So there is a rich structure coming out of these things. But still, there is this problem, which it makes sense. I will say something more precise in a minute. So, I mean, in all this classification, in some sense, if we look at the G-module structure that I mentioned before, that is pretty well understood. I mean, by what I say, this just means that it is well understood what are the weights occurring here, what are the irreducible representation of G occurring here. So this is a direct sum of, say, B. Or what I said before, but this is just, I mean, when they're non-zero, they are irreducible. So what is not almost at all understood is the algebraic, is the G-algebra structure of this ring. So this was yeah, okay. In some sense, we have these irreducible models. We know their highest weights, and we want to multiplicate them. It's some kind of deformation of the tensor product, some degeneration of the tensor product. You want to understand in some way what are the irreducible models that you get multiplying irreducible spaces of functions. So this is the problem. Now I will become more clear and more explicit going on. Okay, so by what I said, there is a lot of combinatorics which allows to control these modules, this coordinate ring, at least on the point of view, I mean, of its G-module structure. So to be more precise, let me fix some standard notation. So we fix, as usual, a Borel subgroup. And we fix a maximal torus. And we fix okay, we have the characters of the torus. I mean, these are all the standard stuff coming with an algebraic group, with a semi-simple algebraic group. So these are the homomorphism of T on C star. And we have the root system. Okay, and also let's fix a base. The base defined by the Borel subgroup. Okay, and it is well known the irreducible representation of G, they correspond to the dominant weights. These are is a monoid inside the character lattice. Okay, so in particular, let's look back at our object. So we have this. So I mean, we said that I mean an important thing coming out of the definition was the set of irreducible representation having a k-invariant vector, because these are those appearing in the coordinate ring. So we have a natural monoid appearing which is the weight monoid of G mod K, of GK. What is this? This is we denote in this way. So lambda G mod K plus. This is the set of weights, of dominant weights, such that V lambda K is non-zero. So where I'm denoting by, if I start with a dominant weight lambda, V lambda is the corresponding irreducible module. Okay, so by the definition, or by the consideration at the beginning, if you want, we have the decomposition. It is isomorphic to the direct sum over lambda G mod K plus of V lambda. So actually, there should be some dual, but we can get rid of the dual because K is reductive. So this is fine. I'm not hiding nothing. It's not a trick. Namely, this weight monoid is precisely the set of weights occurring in this coordinate ring. This corresponds to the irreducible representation that we want to multiply. Okay, also to be more precise, let me write here, not an isomorphism, but let me use this notation. So I will denote by E G mod K lambda precisely the reducible submodule isomorphic to V lambda. But in this way, when I will write E lambda times E mu, this really use the multiplication inside this coordinate ring. These modules lives here, so they have their own multiplication. Okay. So now the problem, to be more precise, the same problem as before, but I will use now some more notation. Given, say, lambda, mu, and nu, these are called spherical weights. In this monoid, so these are weights occurring here. So the question is when does E nu appear inside E lambda times E mu? So here also, when I write this dot, this is not just okay, it's a product, but I'm also taking the subspace generated. If I just take the product of function, this is not a module, so we have to take the linear span of this. So this is by definition, this is the span of the products. Okay, so this is the question, and this question also makes sense because in some sense, and well, hopefully you will understand a bit more of this. This set of weights, in some sense, it behaves as the set of, or as rather as a set of dominant weights of a suitable root system. By G mod K. Namely, we can attach to our pair GK a root system, which is has nothing, it has something to do, of course, but which is different from the root system of G. It's another root system, also of another type, possibly. And this really allows to control combinatorially this set and to describe it. So when I said this set of weights is well understood, this is really understood as the set of dominant weights of a root system, because this is understood. And so, in some sense, what we would like to do is to bring in the picture of this problem, this root system, not just in the decomposition of this coordinate ring, but also in this multiplication issue. In some sense, we want to connect this product to the tensor product of this root system. This is somehow it's going to be what is conjectural in some cases, and also the outcome in some cases. Okay, so we will be interested so in the case, as I said, G simple and GK, a spherical pair, with this root system that I'm going to define in a while of type A. So this partially explains the title. Okay. So, other questions so far? Okay, if not, I will start speaking a bit of symmetric subgroups, because in that case also this root system is very classic, is the restricted root system, or I mean some slight variation of it, and it's more probably it's more is more known. I mean, people is more used to it, and also it's easier to define. I mean, it's more explicit in some sense, the definition. So how much time do I have, just to have an idea?
Maybe 30 to 40 minutes, whatever you prefer. I mean, take as much time as you need.
Yeah, I mean, we started like 4.10 or what?
Yeah, you started at 10, so yeah.
Okay, perfect.
Yeah, don't worry about time. Whatever you need.
Okay, so the symmetric case. So as I said before, we have an involution, theta. An algebraic involution, and the K in this case is the set of fixed point, the identity component of the set of fixed point of theta. Okay, and we also set X as a G mod K, so this will be useful in the subscript. Okay. So how to construct this root system in this case? So first of all, we have to fix a torus A with this property. That if you look at the action of theta on A, then it is just inversion. Okay, so these are called the split tori, and we take such a torus and maximal with this property. This is typically called a maximal split torus. Okay, and then we take all the rest, namely, now we take T, a maximal torus containing A, I mean a maximal torus of G, and we take, so we have all the notation as before, but now we can choose the Borel subgroup containing T. I mean, this is equivalent in choosing a set of positive roots. So I will state a property in terms of the root system. And we can choose the Borel subgroup in such a way that I mean, theta acts also on the set of characters. I mean, because sorry, the T has to be theta stable. I mean, all these exist. I mean, this of course has to be shown, but is part of the theory of symmetric spaces. So we have an action of theta on the characters, and we can choose a set of positive roots in such a way that theta of alpha is a negative root whenever alpha is a positive root and theta of alpha is different from alpha. So this is essentially the canonical choice of a Borel subgroup in this setting. Okay, and now we can define the root system. Phi x. This is the set of characters of the shape alpha minus theta alpha, such that, so this is an extra D that came out, such that alpha is a root and alpha is different from theta alpha. And this is called the restricted root system. Of G mod K. So this is actually a root system. This is a theorem, if you want. It's actually possibly non-reduced. So this is the point. And there is a canonical basis once we have fixed all these things. It is just the set of the images of the simple roots. So we take the simple roots which are moved by theta, and this is the base of the restricted root system. Okay, so some nice properties also in this case is that, so first of all, if you look, let's define lambda x as the lattice generated by, so these are the spherical weights we were playing before, and we just take the lattice generated. So this is inside, it's always a set of characters. And this is identified with the weight lattice, so as I mentioned before. Identified with the weight lattice of the restricted root system. And even more, if you look at the set of spherical weights, so this the weight monoid of before, so this, by the way, is equal to the intersection of the element of this lattice with the dominant weights of the torus. So I mean, the notion of being dominant, these are compatible in the two root systems, and this is identified with the monoid of dominant weights associated to the base that we fixed. Okay, and actually we can also define the co-roots. Given a root phi, I mean, sometimes I'm constructing all the root data, the root datum associated to this symmetric space. And this is just taking the scalar product of, I mean, of the ambient space. Namely, we have a map from phi to, sorry, from phi x to the homomorphism of the weight lattice to Z, sending alpha to alpha check, where alpha check is defined by usual definition. So these are not roots of the group. Now we'll give an example where we see more closely. But these are not roots of the group. I mean, so we are recollecting in some sense the root datum. So at the end, we have a root datum. Let's call it Rx, which is lambda x. So actually, it's not a root datum, but it's a base root datum. Namely, the root datum plus a base, which we can think as this triple. And in general, root data, they correspond to, I mean, if we take root system, they correspond to semi-simple group. The difference with root data in some sense is that the lattice doesn't need to be precisely the weight lattice of the root system, it might have a bigger rank, for instance. So in general, root data are important because they allow to classify reductive group. So the root data, they are really the combinatorial object corresponding to reductive groups. So at the end, we can associate to this root data a reductive group Gx. Okay, so in particular, this lambda x will be the set of character of its maximal torus, of a maximal torus. So actually, in this case, in the symmetric case, this is a bit weird because this root datum is actually semi-simple. So I mean, I am doing something a bit more complicated than what I might do. But in the next case, this is not going to be semi-simple. So I prefer to use this notation. But so in this case, it is semi-simple. Okay, so before giving an example, just another definition. So by what I said, the irreducible representation of Gx, now they correspond to our monoid lambda x plus. So let's, okay. So in particular, so let's recall that the function here is isomorphic to the direct sum of the v lambda with lambda in lambda x plus. Okay, but these are G modules, whereas here I'm playing with Gx modules. So to any lambda here, I can associate also an irreducible module for Gx that I will denote by Vx lambda. And also I can associate, as we did before, let's move this here. And this was V lambda. So this is a G module, and this is a Gx module. Okay. So before stating a first conjecture, let me give an example because probably it's the time. Just to see this root system, I mean, how they are different from the original root system. So let's take SL6 over SP6. So here, of course, G has type A5. And so this is X, let's say phi of type A5, whereas phi X will have a type A2. So in this case, the type is the same, I mean, apart from the rank, but it can also be totally another type. Okay, and let's see closer what, so let's take the omega 1, omega 5, the fundamental weights of A5. So what is lambda x plus? This is freely generated by omega 2 and omega 4. So this is rank 2. Okay, and by what I mean, compatibly with the fact that this root data is going to be semi-simple in this case, but I mean, in the next cases, it will be different. And so what about phi x? Phi x? Well, phi x has two roots, say sigma 1, sigma 2, which are as follows. So sigma 1, I don't want the calendar. Okay. Sigma 1 is alpha 1 plus 2 alpha 2 plus alpha 3. And sigma 2 is alpha 3 plus 2 alpha 4 plus alpha 5. So these are the two, they are called the spherical groups. And these are the elements of this root system phi x. And so if we look, if we take lambda equal to A omega 1 plus B omega 4, then of course we have the corresponding G module of weight lambda. And we have also so Gx in this case is of type A2, is SL2 actually, and Vx lambda is has highest weight. Say A P1 plus B P2. So in this case, it's very simple. I mean, in some sense, if P1 and P2 are the fundamental weights of A2, then the map is quite easy. It's just is defined by omega 1. Sorry, omega. This was omega 2. Sorry, omega 2. So the map is omega 2 goes to pi 1, and omega 4 goes to pi 2. Namely, omega 2 goes in the fundamental weight associated to sigma 1, and omega 4 goes in the fundamental weight associated to sigma 2. I mean, it's just a matter of checking the pairing. Okay.
Sorry,
Yes.
maybe the notation should be delta x instead of phi x. It's the base
Yes.
of the root system.
Thank
right?
you. Yes. Absolutely. Yeah. So the root system is these are the simple roots of the root system. We have two roots generating this A2. So we have their sum, for instance, also is going to be an element of phi x. Okay, so let's come to a conjecture.
So, Jacopo, I have a question. So for, in
Yes.
general, this SLSP family of examples, is it easy to say what the root system is?
Yes, is essentially the half. Is a n over 2, but so this is a5. So you have to take. So if you do SL 2n, then you take 2n minus 2. You divide by 2, and that's the rank, and then it's of a type A. So, but essentially, it's the half of the root. Is type A n over n minus 2 over divided by 2. Yes.
Thank you.
Welcome. So it fits in our case. We have this conjecture. So this is, well, first of all, before stating it, just to give some attribution, so in some sense, it follows quite easily from another conjecture of Stanley. Well, I mean, easily. You need some technicalities, but they're kind of classical things. And this conjecture was formulated by Stanley in 1989. And this was also considered, I mean, in this, so this conjecture is about Jack polynomials. So I don't think I will go in speaking of Jack polynomials because it will take me a bit away from the path. But in some sense, this is quite a rough incarnation of this conjecture. I mean, Stanley's conjecture is way more general, way more strong. And this formulation that I'm going to give was also considered in sort of an equivalent form also in a paper of Graham and Hunziker in 2009. But I mean, in some sense, the beginning is this conjecture of Stanley. And the conjecture is as follows. So suppose, so we are always in the symmetric case. So suppose that phi x, so let me write x, so this is a symmetric of type A. And so of type A with, so to be more precisely, with phi x of type A. Okay, and take 3 weights as though we want to multiply. Then E lambda times E mu contains E nu. I mean, this inclusion is equivalent to the corresponding inclusion for tensor product of phi x, as I mentioned before. So in this inclusion, okay, this is more clear. That on the right hand side, it's a bit more. I mean, just I mean that if you take the tensor product, then the inside you have an isotypical component of high weight nu. I mean, you have a non-trivial projection on this subspace. Okay. So just a few words. but I mean, I don't want to say very much, but in some sense, so what are Jack polynomials? So Stanley, in some sense, speaks about the multiplication of Jack symmetric functions. And also has a Peary rule for this. So I don't want to go not at all in the details, but in some sense, so Jack symmetric functions, they are one parameter symmetric functions. And we can, in some sense, encode this multiplication problem, this G-algebra structure inside the spherical functions. The spherical functions are the decay invariant function here. Namely, in EX lambda, we have we can take the K invariant subspace, and this is one-dimensional by what I said before. And the spherical function in some sense are this function. We just take some function here, f lambda. Non-trivial, non-zero, of course. And so at the end, the algebra structure of our coordinate ring is encoded in this invariant ring. So where I'm taking invariants on the left. And the point is that so Jack symmetric function, they have one parameter. If I specialize this parameter at 1, I get should function of the corresponding root system. If I specialize this parameter to some suitable value, which is prescribed by, for instance, a symmetric space, then I get these spherical functions or some variation of it. I mean, it's not clear at all from what I said what has to do a spherical function with a symmetric function. So in a sense, I will have to restrict this function to a suitable torus, and I will get a symmetric function, which is at the end is a specialization of this Jack polynomial with on another value of the parameter. So this is the connection, and Stanley has this strong conjecture, this positivity conjecture about the multiplication of Jack symmetric function, and we can just specializing the value. So we are losing a lot of information in this conjecture. We can obtain a conjecture which sounds like that. Okay. And what about, so we are very interested in this Peary rule, because the Peary rule, the conjecture above, in case it's true in case phi x is of type A1, thanks to the Peary rule. So this is fundamental. So this conjecture that I stated here is true if phi x has type A1. Okay. So now let's go to the, let's increase the generality. So let's consider, and this is essentially this is what we do. So this is the main point of our paper. Let's consider the non-symmetric case. So again, we have G simple and GK reductive spherical pair. Okay. Again, we denote X G mod K by X. And by what I said at the beginning, we have this decomposition. The function over X, these are direct sum of these modules, EX lambda, where lambda is in this monoid. Okay, so a problem of this non-symmetric case is that this root system, which still exists, I mean, the definition is a bit more intricate. It's not hard to give it, but it's an important theorem that this is produces a root system. And this definition I'm going to give goes back to Knop, and it's also very connected to our problem. So again, we denote by lambda x the lattice generated by lambda x plus. So this is always inside the character of the torus. So, and we have this notion of root monoid. So this is mx. And so it's very close to our problem because we just take the difference, lambda plus mu minus nu. So this is is generated. So it's okay. So this is the semigroup. In the character lattice generated by the differences lambda plus mu minus nu, such that lambda, mu, and nu, they correspond to some irreducible component in our coordinate ring, and E nu appears inside E lambda times E mu. So in some sense, this measures the complexity of this multiplication. It measures how much this multiplication is different from its top component, which always there, and which gives just the zero root, in some sense, the zero element of the root monoid. Okay, so this is just the definition, and the theorem. So this is due to Knop in 96, and also there is some addendum due to Adviev and Coupi-Foutou in 2018. So I will combine something inside the Knop statement. So the first statement is that this is a free monoid. And the second point is that let delta x be the set of free generators then delta x is the base of a suitable root system. Of course, all of these respect to the pairing of the inside the weight lattice, which is phi x. But of course, I mean, the definition is much more, is much less direct than what we had in the symmetric case. So this is the same. So if x is symmetric, so I'm using the same notation. This is a bit wrong. I mean, because before this is by definition a restricted root system. Sorry, a reduced root system. Whereas before, the restricted root system was not necessarily reduced. So, I mean, the point is that this is, in a sense, is the reduction of the root system of in the symmetric case. Then this root system is the reduced form of the restricted root system. Okay, but since, I mean, we're interested in the type A case, these are really the same. So in type BC, one has to be a bit more careful. Okay. So again, so we have, so lambda x as before. So this is not the weight lattice of phi x, because for instance, the rank of lambda x might be bigger than the rank of phi x. So it's not the weight lattice in the sense of root systems, but it is the weight lattice in the sense of root data, because we have still a pairing. We have co-roots. Namely, we can map the roots in this root system in elements of the dual lattice. And the definition is very natural, it's always the same. Okay, so again, we end up with the root data, with the root datum. But now it's really reductive. I mean, not necessarily semi-simple. We start with X, which is G mod K. We have this root datum Rx, which is the triple, so it's a based root datum again. Lambda X, delta X, delta X. So these are just the simple co-roots. And this determines a reductive group GX. If you want, with a Borel subgroup. Okay, and again, as before. So lambda X plus now doesn't really coincide with the dominant weights of this root datum, but at least it's contained there. Is contained in the monoid of dominant weights. Of Rx. So given lambda in lambda X plus, we can associate a module Vx lambda, which is an irreducible representation of Gx. So, and the claim essentially I want to state is the same as before. So before, let's give an example of a non-symmetric example. Okay, so we take X equal to SL5 over SP4. So it's not that different from before, but the group has increased. Now it's SL5. Before, I mean, the symmetric case would be SL4 or SP4. But things change in this case. Okay, so now what is lambda X plus? Well, this is the full set of dominant weights. This is omega 1, omega 2, omega 3, omega 4. So if you want, it's equal to lambda plus. I don't remember if I give this notation, but you understand. Okay, and phi x is of type A2 times A1. What are the roots? Is equal to sigma 1, sigma 2, sigma prime, where sigma 1 is alpha 1 plus alpha 2, sigma 2 is equal to alpha 3 plus alpha 4, and sigma prime is equal to alpha 2 plus alpha 3. So if you look at the pairings, sigma prime is orthogonal both with sigma 1 and sigma 2. So these will form an A2, and this is going to be A1. Okay, and what about the map between weights? If I take lambda in here, so just a weight, say lambda equal to sum of ai omega I, then the corresponding weight of the root datum is A1 plus A2, so pi1, so we will use the same notation as before, plus a3 plus a4 pi2 plus a2 plus a3 pi prime. So pi1 and pi2 are the fundamental weights corresponding to sigma 1 and sigma 2, and pi prime is the fundamental weight corresponding to sigma prime. But we see that before things were straight in some sense. Now things get mixed in these different components. So this is a big part of the, it's a big point in how things change from the symmetric case to the non-symmetric case. Okay, so I can state the conjecture. So suppose that phi x is of type A. And the conjecture is really the same. It's, x nu is contained inside ex lambda times ex mu, if and only if vx lambda tensor vx mu contains vx nu. So just a short remark. So when also if we take X symmetric, we have some extra cases in this setting, because for instance, we can have symmetric varieties with a restricted root system of type BC1. BC1, since this is going to be the reduced version, then phi x is going to be A1. So this includes also symmetric varieties with root system, say restricted root system of type BC1, which were not included in the former conjecture. And then the theorem. So I didn't say this at the beginning. So all of this is a collaboration with Paolo Bravi. So this is together with Paolo. So essentially is as before. So first of all, we have to exclude a case, which is a symmetric case. Suppose that X is different from F4 over B4, which is symmetric of type BC1. But in some sense, we cannot apply in this thing something that we can apply in every other case. Then the conjecture above, the conjecture is true if Stanley's conjecture is true. So we definitely expect this conjecture to be true. And secondly, again, if the conjecture is true, if every, say, irreducible component of phi x is of type A1. So we already show an example. So in the symmetric case, the root system are always irreducible if G is simple. In this case, we already saw an example which was A2 times A1. So for instance, just to see another example, if we take the triality, so SO8 over G2, then phi x is of type A1 times A1 times A1. So we can, for instance, apply the theorem in this case. Okay, so this, but I'm close to the end. So I can either stop here So first of all, are there any questions?
So maybe this is a good place to stop, and then we'll ask some questions. Is that okay?
Sorry?
So maybe this is a good place to pause.
Yeah.
We'll ask. Yeah. So let's
Yeah, yeah.
first let's like everybody thank Jacopo for that great talk.
Okay, thank you.
Now I'm gonna stop the recording for a moment.